Okay, everyone. So once again, we're going to one of these rigid bar examples. So this bar right here, it is rigid. These other two, they can stretch or compress. And as you can see, this time, they're not stretching or compressing together. They're actually, one is going to stretch, the other is going to compress, or vice versa, depending on what our load is. So this is a much more difficult problem. Now, what does it want you to calculate? Well, knowing that the normal strain in rod 1 is going to be negative 570 microstrains, means it got compressed. It wants us to find the normal strain in rod 2. The normal strain in rod 2 if there's a 1 millimeter gap in its connection, and normal strain in rod 2 if there's a 1 millimeter gap in this connection. Okay, so it's got a very similar case here. However, you're going to have to do some geometry because they don't stretch together and compress together because it's stuck here. It's going to turn. So that is going to make a big difference. Now, let's look at this again. I will give you this one hint that it's going to be similar triangles. Similar triangles are going to be very, very helpful for you in this regard. So if you know how far down it is here, and you know what this distance is, then you should be able to figure out how far down it is here, given this distance, okay? Similar triangles. Look at the ratio. This length over this distance will be equal to this length over this distance. Okay, now go forth. Grab a friend, grab a rubber duck, grab the traveling gnome, and see if you can solve this problem. And then come on back. So 3, 2, 1, and we're on to try it ourselves. Let's do it together. So first off, from the strain given the rod 1, we can figure out its compression. Okay, it's not elongating this time, it's compressing. We had 570 microstrains, and its original length is 900 millimeters, and it got shorter by 0.5130 millimeters. Therefore, that joint at B moved down 0.5130 millimeters. So if we're going to figure out how far B went, we have to use those ratios. But you can see from this little right here, these are two similar triangles, one right there and one right there, and therefore the ratio of their length to height, or their slope, as you could say it, would be the same. So we know what VB is over 240 millimeters, and so we can then connect that to what VC would be. We plug it in, we get that VC would be moving 1.2825 millimeters down. So you can see that it moved far more than VB did, and that's because of how these are all connected. So how you build your system is going to affect how it strains, how it stresses within that system. Okay, now if we have this elongation for the second one, then knowing its original length, we can calculate the strain on it. And once again, it looks like my micros just all broke in this. So I have to go back and fix all of those. That's okay. I can write them in for now. So 855 microstrains. Now, in the second situation, we have a 1 millimeter gap at C. Now that doesn't affect rod 1, therefore its elongation is going to be the same, and we'll still see that the joint C moves down by 1.2825 millimeters. However, even though the joint went down that far, it doesn't mean that the member elongated, because it's going to have to move 1 millimeter before it even begins to elongate member 2. Therefore, the elongation is far less. It's at 1.2825 minus 1 millimeter. And the reason for this is because the gap is over here, not over here, so our triangles stay the same, at least when it comes to deflection. Okay? Now, this is obviously far less, and so you can see that the strain in this rod is going to be far, far less than it was before. So we plug it in and we get 188.3 microstrains. 188.3 microstrains. Now, for part C, we know that the strain given by rod 1, that the elongation, or sorry, contraction of rod 1 has to be this. This doesn't change. But in order for it to be able to move this much, we'd have to move it down further because there is that gap. There's a 1 millimeter gap before that's able to be compressed. So even though we're compressing, you're like, well, when did it hit it immediately? No, just imagine that it's inside of this little room and it can go up or down before it actually begins pushing on this rod. So VB is actually 1.513 millimeters, and this is devastating. Okay, this will be absolutely devastating to this last rod. We're going to see why in just a moment. Because it is similar triangles, and so whatever this is, whatever increase we have here, would be a massively greater increase right over here. So we use our similar triangle just like last time, and we see that that's now making it stretch by 3.7825 millimeters. It is a massive increase from before. Before, didn't have that one. It was much, much smaller. But now we have increased it greatly. And that is also going to increase the strain. So it's 2,520 microstrains. Okay, that is a great, great increase and would most likely cause its failure. Let's go back and see how much it was originally. And it was 855 microstrains originally. So this tripled the strain it is feeling. It tripled it because of a 1 millimeter gap. So small things can lead to devastating effects, and you are in charge of that as an engineer. Now, normally we have large factors of safety, so things like this would not cause it to be destroyed, but we still have to be careful. And also, a lot of redundancy is built into different structures. Okay, but please remember this. Remember that we use similar triangles to solve these kinds of problems, and that our rigid bar right here is completely rigid. And we also assume that even though it's a rigid bar and it would probably be moving slightly to the left here, that it just goes straight down. That's the only way you can solve these problems, at least simply. Okay, with that, we're going to stop right there, and I will see you all next time as we jump into shear strains and other types of strain that you will encounter. So, have an absolutely wonderful day. Bye-bye.